about whatever I'm interested in. Whereas a cluster, I might end up doing that as a part of a convenience, but I'm actually getting all of one group because of the way that I sample, which might help me learn more about that specific group too.
So then convenient would just be more of like a random selection. Cluster would be more of a specific.
That's true. Yeah, convenience might have a more random component. But maybe not a random component that you understand, right? Like you don't necessarily know the groups that anyone that you talk to represents themselves as, because all you do is ask them about your survey question or whatever you're interested in getting from them. Whereas the cluster, you're like, I know all of these individuals have this component. Yeah,
so the number 3, you said, for example, 300 people, you choose 100 people. Is that 100 people has to be faced by, front of you or be anywhere?
Yeah, so the idea, so simple random samples are really hard to do. Part of it is, so you can imagine, let's say I do have a listserv of all students. So I have all students from the university, and I have everyone by their student ID number, and then attached to their student ID number, I have their email. And therefore, I have this survey, and I want to get an actual simple random sample of students to answer my survey questions. Okay, so what I do is I have a random number generator. It picks which rows I'm going to choose as my students of interest, or it picks which IDs that I'm going to choose. Does that make sense? Okay, so I randomly choose 100 people via the row that they're sitting in. And then after that, I have their email addresses, so I email those 100 people and I say, you were randomly selected to take my survey. And if you choose not to respond to me, now you've broken my simple random sample, because I have to go find someone else, and now it's not random, because you were selected and you chose not to answer. Does that make sense? So now it's not random anymore. Now you have volunteered not to give your information, and my simple random sample is broken. Is that idea? Yeah, go ahead.
For number 5, you said like every group gets a percentage. It's like if you're asking about like politics, you want to collect information from women and men.
Yeah,
Say,
or maybe all political parties, right? So like Democrats, Republicans, Independents. I want to make sure that I accurately represent all political views via that. Or if I'm asking about something that actually has a gender-related component, I want to make sure that I accurately represent all views. So I make sure that I get at least so many of this group, and so many of this group, and so many of this group. Is that okay? So in picture form, I imagine cluster sampling is like, imagine this box is everyone of interest. This is my entire population. And you can imagine basically they're divided into groups, and a cluster sample is essentially just choosing all of one group. A stratified sample is also having individuals divided into groups, but then I might go in and choose 6 people from every single group. Okay, so I make sure that I accurately represent all groups via sampling from within each of those groups. Is that idea?
so how's cluster is not like biased?
It could be. It depends on the question.
Okay.
Right? So, again, going back to the 2010 question, like, if I was interested in how many individuals wanted a coffee shop in the lobby, maybe asking all 2010 students isn't biased on that. Is that okay? And then systematic, I imagine just being like, I choose this group, then I choose this, then I choose this, then I choose this. It's like some fixed interval in which I'm choosing my samples. And then random sample is like, I just go in here and I select. And then essentially with these two, I imagine that I kind of live in one corner, and I kind of just select the individuals closest to me. This is how I imagine all of this sort of working out in picture form as a visual person. So, this is okay? Makes sense to everyone? That works. All right, so I think there's like maybe 1 or 2 questions on the homework that are about sampling methods. And they're listed in the lecture notes, but it's something we should talk about. It's worth noting that if you don't take a good sample, if you don't take a truly representative sample, any inference you try to draw towards your population is not good. You take a bad sample and you try to make claims. If the sample is bad, those claims are wrong. Anything else about the homework? Anyone want to remind me what we talked about on the grade?
Sampling distribution.
Distribution. That's right. We talked about sampling distributions. And who remembers what a sampling distribution is? It's the distribution of a statistic. That's right. So it's the distribution of a statistic. And in particular, we said we were going to focus on one particular sampling distribution. What sampling distribution are we going to focus on? Yeah, the one for the sample mean, right? So a mean is just a statistic. And the idea is that we're going to focus on the sampling distribution of the sample mean. Is that okay? Okay. So we introduced two theorems last time too. Does anyone remember what those two theorems are? Okay.
Law of large numbers.
Law of large numbers and the central limit theorem. Okay, so what does the law of large numbers tell us? What's the high level? What is it given?
As we approach infinity for our sample, the sample mean will will get closer and closer to our actual mean.
Yeah, that's right. So we get a larger sample size, and the sample mean will be a better representation of our population. Okay, so the sample mean converges to the population mean as our sample size increases. And then the central limit theorem is a little bit more confusing, and that's what we're going to actually spend a good part of today sort of introducing an activity where we'll see how the central limit theorem works in practice and like what it's doing. So I'm not going to jump into that now. Instead, we're just going to go into this activity. So there are going to be two worksheets that go around. One looks like this. You're going to be working in groups, preferably maybe groups of 2 or 3. If you want to have a group of 4, that's fine too. But preferably maybe around 2 or 3. Every group needs one of these. Okay, so every group needs one of these. Every individual needs one of the other worksheets. So the other worksheet looks like this, and every single person will want one of these. So, okay.
Every group needs one of these. Trying to be my group.
So only, so if you have a group, only one person per space. Yeah, of that. So that's okay. You can just pass that. You just won't need that. Okay. And I'm guessing a group somewhere in here.
Are you guys a different group?
So 2 or 3. Somewhere here.
You're correct. All right, so I think there's a sample that we want to go last. I didn't want to be dealing with that.
Okay, so the first thing that we will do is you're going to use, amongst the group, this sheet will not look like this. You will roll the die twice. You will roll the die twice. Pick your die roller carefully. And essentially, the first time you roll, that will be whatever number you see. So it doesn't really matter, but one of the ways will be the column that you're in. And then the second time you roll, it will be the row that you're in. So you're going to roll the die twice, and where those two things match. So if you roll a 6, and then you roll a 9, and then you go to 75, 75 will be the first number that you choose in your sample. Is that okay? And if you roll again and you get a 0, and then you roll again and you get a 2, that'll be the second number in your sample. Does that make sense? Any questions about that? So you will do that and you will get 5 numbers and you will average those 5 numbers together. Then you'll do that again 5 times and then you'll average those 5 numbers together. And then you'll do that again and then you'll average those 5 numbers together. Is that okay? Okay, cool.
I'm lying.
You wanna roll?
Sure. 4. Wait. Come on. 4. 70. 6. 4. Are you kidding?
Wow. What's the probability of that?
No, I'm
That is.
pretty good. Right?
5. So now we're doing sample 2.
Can we do all of them? Every box?
2, 3, 7.
I'm a little over this, I'm not gonna lie. I'm not digging the 4s right now. 5.
So we're recording really soon.
Yeah, do all 4 right away. Yeah, all 4.
Oh, 5 and 1. I'm sorry.
73?
Yep. Oh, wait. Okay. Oh, never mind.
Right?
Yeah.
Yeah?
8, 5.
6. 67?
Did you have to drive to get up here or did it fly out?
The golden retriever? No, my parents still live back there.
Oh, do they?
And her parents live out there. So she do
4 and 4.
The other one where she got
Oh, really?
dog is
My phone's about to die.
my thing is all on your way.
I really need to go out because I want to
They learn
dog.
My parents have one of those dogs. They sees eating it like
Do those numbers?
like cows and horses. And like hanging out their friends with dogs. Yeah, they have to fly me home to watch it. My stepmom has a little bit too kind of a All right.
Our golden retriever got
Oh, it's an ugly dog. 2 months. So he was weird. So did he bring
Well, so yeah, you can try it. Shoulder's kind of like
Okay, I've gotten a different number every time I've done this one.
you're one.
Yeah, that's great.
Can I get the same number? 70 plus 70 plus 70 plus 65 plus 70 divided by 5. There we go. I assume we go up and
We'll double check here.
Yeah, but I did
Good.
Is that good? Do you want me to go or you want to?
Good. All of our samples are really good.
Sorry. I don't have a super
Are you?
I work retail. It's not. I've worked a few different kinds of retail. Like I used to work at Off-Broadway Shoes, where it's kind of like you just pick up after people. And I used to work at Express, where like they're actually helping people find things and like find outfits for things. Now I work at Coast, where like I'm not selling, I'm hosting is what we call it. So
Is it the outlet or the store? Where at?
Park Medical.
We have Gucci I'm doing, in my marketing class, we're studying luxury brands. I didn't even know it.
Yeah, we're all about like Coach's all about like luxury and what it means to like host sell them something, and everybody always asks us like where their price tags are. We hide all the price tags for like fall months product, not the price. Yeah.
Once you go to the outlet, they give you a half off.
Right.
Do they really show you the price?
But it's different quality.
Yeah, also, evidently the Gucci is different. But it's not, you know, it's not
Right.
The real shit you store in there.
So let's go through some
All
of the
of our
questions on the
materials.
second worksheet. So the first question says, when you drew the 5 salaries, this was an example of a random sample. That's right. So, and it's about as random as it gets, right? Any one of those numbers on the grid has an equal chance of being chosen, because 0 through 9, all equally likely, you rolled it twice. Any one of those 100 numbers equally likely to be chosen. Does that make sense? So we had a random sample. When you took the average of the 5 salaries, this was an example of it's a statistic. That's right. So every one of those averages is a statistic. Okay? And then if I took the average of all 100 of those salaries, so assuming that these are salaries, but whatever, if I took the average of all 100 of those numbers in the middle, what would that be an example of? The parameter. That's right. So the parameter would be if I took the average of every single number in that grid. Does everyone see how that's the case? So my box, from what we were doing before, is like all 100 of these numbers. And then what we're doing is we're taking 5 of them and then averaging. And then taking 5 and then averaging. And taking 5. Okay? Did anyone get a sample mean that match in the first to second? No? Okay. Take your time. All right. So then on the end it says, what is the distribution of all the sample being called? So that is, what is this distribution called?
Sample distribution.
This is the sampling distribution. That's right. So this right here is called the sampling distribution. This is the sampling distribution. And specifically, right, so if you remember, sampling distributions are the distribution of a statistic. And specifically, this distribution is the distribution of x bar, where n is equal to 5, right? So this is like, you write it this way. So x bar, where n is equal to 5. So this is the distribution of our sample mean, or the sampling distribution of x bar, where our sample size is 5. Right? Does that make sense? Because we took 5 samples to get each mean, right? And we took 5 samples and we got another. So that has nothing to do with the 4 that you got on your page, because that happened over and over, and that happened for every x on this grid. But it happened via a sample size of 5 for every single mean that's up here. So, okay. So, what's the shape? What's it look like?
Sample size.
That looks pretty normal to me. It looks pretty bell-shaped. It looks pretty normally distributed to me. But, yeah. So, in our case, if you remember when we talked about the central limit theorem, I said, well, the sample size that we use in this class, the textbook example, is that the sample size should be 30 or more. But in our case, we actually, even with just a small sample size of 5, got something that was fairly normally distributed. A lot of that has to do with the fact that if you plotted all 100 of these numbers, that's fairly normally distributed as well. And that's why it didn't take that large of a sample size. Okay, so one of the other things that I want you to sort of see, I wrote the grid from 60 up to 80. And if you look at like the the numbers that are just within the table, I think the smallest number is 60.
Yep, that.
Yeah, 40. And then I think the largest number is 78, maybe?
I see 78.
78. Where's 78 at?
2, 1. Or 1, 2.
Oh, okay. Yeah, 1 and 2. So, so you'll notice that the spread of the original data goes from basically the start of my grid to the end of my grid. But when we take the averages, it shrinks in around whatever the mean of the original distribution was. So if you actually average all of these numbers together, I think the true mean is like somewhere in the low 69, high 68 range. And you'll notice that the largest bars are right in that range, right? Like in the high 68s and the low 69s, and those are the two highest bars in our histogram. Does that make sense? Because if you were to take the mean of all 100 of these values, that's actually right in this range where those two bars are at. Does that idea make sense? So the sample means tend to converge around that population mean. They tend to converge around the mean of all 100 of these values. And the spread, if we were to take a sample size of 10, would shrink down even more, it'd be even closer to that. And if we took a sample size of 20, it would shrink down again even closer, so that everything's sort of falling, so even closer to whatever the mean is of that entire population. Does that idea make sense? That the spread that you're seeing is because our sample size is 5, which is still a lot smaller than the spread of the original data. Does that make sense? So the larger that sample size, the closer these things will fall in to just that one point. Then these last ones are a little bit hard for us to answer because I didn't actually calculate the mean of the original 100 draws. But it says, what is the mean of this distribution? And the way that I would answer that is, it's the same as the mean of all 100 of the draws. The center of this distribution is the same as the mean of all 100 draws in that original grid. Does that make sense? So the mean of this, the center of this distribution, somewhere in this area, in these two bars, is basically, so you might write something like mu of x bar is equal to mu of x, where x is like all 100 of the draws, and x bar is the mean of this, mu x bar is the mean of this distribution. So yeah.
So is it like the median is equal to the mean?
And in this case, the median would be equal to the mean, even if in that original distribution that wasn't. Because it's a normalized distribution.
Why is there n equals 5 and you have x 5 over there?
This is just keeping track of, yeah, so this was just, I wrote these as an example of where I marked them over here. So my first x bar, so you had 4 of these.
Oh, okay.
Yeah. Okay. Yeah, so this isn't keeping track of the sample size. It was just saying, I got 5 numbers, and then the first average that I got of those 5 was this.
Okay.
And then the second average that I got of those 5 was this. The variance would just be that formula that we looked at in like week 1.
Mm-hmm.
So it'd be take every single number,
From the
subtract them from the mean.
yeah, from the mean average.
So, are we asking about the next? What is the variance of this distribution?
Yeah. I was calculating it from.
So if we had the variance of the original data set, so if you took the variance of all 100 of those numbers, the idea is that the variance of this distribution would be that divided by your sample size. Okay, so the variance of x bar, right, the variance of x bar is equal to the variance of the original data. So if you just took the variance of all 100 of those numbers and you divided it by your sample size, that would equal the variance of this distribution. Yeah. I'm not sure how much that is, but you can imagine just plugging in all 100 of these numbers into Excel, ask for the variance, and then you plug them in.
What is that 5 again?
N equals 5
Yeah.
is the sample size that we chose, right? Because it's,
So we only have like 4
Yeah.
so you took 5 draws to get that mean, and you took 5 draws to get that mean, and you took 5 draws to get that mean. So it has to do with how many things you sample to actually calculate that average. Because this, I mean, this is clearly way more than 4 or 5. It's not even the 4 that you had, because it's your 4 with someone else's 4.
So we would have 4 variances.
So we would just calculate a single variance for this distribution. 5 is n.
I know that, but I mean,
The 5 numbers are the 5 numbers you use to calculate the mean. Yeah. So your 4 is irrelevant in this picture, right? Because your 4 might be this one and that one and that one and that one. And someone else's 4 is another set of x's. What's consistent about how all of these x's were calculated were 5 draws went into every single x, right? And that happened regardless of which x you're talking about. So, yeah. Okay, and then what's the standard deviation of this distribution? That would just be the square root of this thing. So, be the square root of it. Okay, you just take the square root of that entire variance. Okay. Sorry. You guys should know that. Any questions about this? So the biggest takeaways, or at least what I hope are the biggest takeaways. Go ahead.
I just can't see. Is that mu x bar?
Yeah, so mu x bar is equal to mu x. So that is the mean of the sampling distribution is the same as the mean of the original data. And then here, the variance of this distribution is equal to the variance of the original data divided by 5. That's what this part says. And then this last part is the standard deviation of x bar is just equal to the square root of this thing. Okay, so, and we'll see this over and over again next week, but hopefully, the biggest takeaways are the larger the sample size, the less the spread in this distribution. The more they sort of like crowd around the true mean of the distribution. The larger the sample size, the more we can be sure that it will follow a normal distribution.
Sorry, the larger the sample size, is more distribution?
The less spread there is in the distribution, right? The smaller the variance. And then, in general, this thing's going to center. The sampling distribution will be centered on the same thing as the original data. Okay? So wherever x is centered, the sampling distribution will also be centered. And hopefully that's sort of illustrated by this example. The other part is just understanding what a sampling distribution is talking about. So recognize the way that this was calculated. We took a sample, we took the average, and we took a sample, we took the average, we took the sample, we took the average. And this is the distribution of all of those averages, right? It's the distribution of a statistic. So yeah, go ahead.
I've got the mean for all that.
What was it?
16 or 69.19.
Okay, 69.2, basically. Yeah. So you can see it basically centered right where this smallest bar is. Okay, does that make sense? So, thank you for building that credibility.
Same thing with the variance and the standard deviation, if you want that.
Yeah, so what did you get?
I just put all the numbers in a list and did a stat calculation.
Yeah, so what's the variance? This will help me for my next two
Well, I
sections.
calculated the standard deviation first, and I did the variance.
Okay, so what's the standard deviation?
It's like 3.75.
3.75. Okay, so if you were to take so this is the standard deviation. This is like, I might notate this as sigma x, and I might notate this as mu x. So the idea is this should be the same as the center of this distribution, but the original spread was at this, whereas the standard deviation of x bar is basically going to be equal to 3.75 over the square root of 5. So this is the standard deviation of our new distribution. Does that make sense? And if I squared all of that, right? If I square 3.75 and square 5, then that will give me the variance of this distribution. So, okay.
14.06, the variance.
14.06? Okay. Sorry. All right. The actual values themselves will.
Well, if divided by 5, right? And we could just, the standard to be 3.75.
So that's going to be the variance of x. It's going to be the variance of the original 100 draws. Variance of this distribution is different.
Okay, all right, do you square root the whole thing or just 5?
So you're square rooting both parts, but he gave me the standard deviation, not the variance. Right, so I just wrote the standard deviation. That's already square rooted. And then I square rooted the denominator as well. So math that. The square root of x1 over x, well, let's say the square root of 25 over x is equal to 5 over the square root of x. So that's what I get over there. The idea is that 3.75 is already the standard deviation. It's already square rooted. So it's already like 5. So I just divided it by the square root of the sample size. Cool. Any other questions about this? So hopefully it just gives you an illustration of how sampling distributions work, because we'll be doing mostly problem-based stuff with this in the future. So this is just to like build your mindset of what we're talking about. Go ahead.
So for the grid, does it matter how those numbers were got, like how we got those numbers? Because we were given the grid.
Huh?
So how do we know that like these numbers were random to be random?
So you could put the numbers in whatever order you want in the grid, right?
Okay.
And the idea is you roll the die to choose them randomly.
Okay.
So the fact that I put them in whatever order is on there, if the order completely changed, because you rolled the die to pick it, and the die is random, it doesn't matter. Right? 0, 0 is just as likely as 2, 7.
Okay.
Okay. Any other questions about this? All right. So with the last 20-ish minutes, I have a worksheet. It has 5 parts on it. I'm going to collect these, so if you work with someone, you can all work on the same sheet. You want to work in the same groups, or you want to work by yourself. Whatever way is fine with me. You can all turn in one copy, just put all of your names on it. So if you work with somebody else, just make sure you put all of your names on it. Those are yours. Yeah, or recycle notice that this worksheet doesn't use any of this good stuff. It's all about numbers. It's all about numbers.
Oh, I'm sorry. Just kidding.
And I will also take the die before you leave, although everyone else is yours. I just can't You can buy like 100 packs though, of like all different sizes.
I'm a dice roller. I love D&D and all this different. I'm actually doing a it's basically Star Wars D&D, and how it works out is that they made their own special die, but it's really story based.